Good morning. It is Monday, November the 16th. Here we are at AP Chemistry at Spain Park High School. As we're going through this Princeton review, this one is not in your version. Okay? It says the following diagrams show the Lewis structures of 4 different molecules. Which molecule would travel the farthest in a paper chromatography experiment using a polar solvent? If you have a polar solvent, now remember, paper chromatography is you have the solvent, you have the substances on chromatography paper, you put it in the solvent rises up. Which one is going to rise up the most with a polar solvent? The most polar one or the most non-polar one? The most polar one is going to rise up the farthest with a polar solvent. If it was a non-polar solvent, the non-polar one would rise up the farthest. So you just pay attention. So we want to find which one of these is the most polar. Methanol. It's a small with an OH. Okay? We know pentane is totally non-polar, only LDS. Okay, this does have an oxygen, but it doesn't have the OH on it to make it as polar. And this has the oxygen in the middle again. Both of these would be slightly polar, but this one's going to be really polar because of the OH. Okay? So that's what you need to know. Remember, the RF factor is the difference between how far the substance goes divided by the total distance of the solvent. Okay? And so when you measure just from the top of the surface of the solvent, you know, or actually you probably measure from where they have the chemicals on the paper, because you're comparing how far the solvent went from that point to how much the individual substance went. All right, that's just a little flashback to chromatography. What number is this for you? 3. That's a good one to do next.
It's not the same room.
It's not?
Is it?
Lewis diagrams for nitrate and nitrite.
Oh, because it looks weird.
Okay? Choose the statement that correctly describes the relationship between the 2 ions in terms of bond lengths and bond energies. Now, what do the double arrows mean? Resonance. So what do we know the bond order is on these? 1 1/3, whereas on this one, 1 1/2. What happens to bond length as bond order increases? If it's shorter, it decreases. Okay? So, nitrite has, and so 1 1/2, so are these bonds stronger or weaker than these bonds? Stronger. Now, what do we know about these 2 bonds? Which one's stronger? They're equal. Why are they equal? Because that's what resonance, the electrons get delocalized. That's the whole point of resonance. These 2 bonds are identical in strength and characteristics. All 3 of these bonds are identical. They're stronger than a single, weaker than double. They're all about 1 1/3. When you have resonance, the bonds that are involved in the resonance are all identical. Okay? So, nitrite has longer and stronger bonds. It has stronger bonds, but are they longer? No, they're going to be shorter. Nitrite has longer and weaker bonds. No, they're shorter. Nitrite has shorter and stronger bonds than nitrate. Yes. Nitrite has shorter and weaker bonds. No. So you can eliminate, because we know bond order, 1 1/3 versus 1 1/2. This is a stronger bond, but and a shorter bond length. Is everybody comfortable with that?
Yes.
You got to look for resonance. What was the next one you did? Oh, it's over here. I don't know. I got to get you a number 4. Okay. What is the molecular geometry of structure A? Okay?
Tetrahedral.
On an AP test, you just have that memorized, but we know it's, what's the AX formula? AX4, okay? So it's tetrahedral. You will have the little cheat sheet, because I'm just way too easy on you, okay? On tomorrow for the test. Now, what's the SO bond order in structure B? Okay? Now, in structure B, okay, how are we getting the bond order? What are we assuming? 6 bonds in 4 places, right? Okay? We're assuming the resonance because we just as easily could have put the double bond here as we did here, put the double bond here as we did here. We have choices. Okay? So that means the reality is the pi bond's getting evenly distributed amongst the whole thing. So we're going to say 1.5. Now, which of the following statements regarding structure B is true? The double bonds must be located opposite to each other due to additional electron-electron repulsions. It is more polar than the molecule represented by structure A. The bonds in the molecule are weaker than those in structure A. And all bonds in the molecule are identical to each other. Which one did you choose? Why?
Because in resonance, they're all the same.
With resonance, all the bonds involved in resonance are the same. Okay? All the bonds involved in resonance. Now, the reason why I'm saying all the bonds involved in resonance, HNO3. I have nitrogen, oxygen, oxygen, oxygen. I put a hydrogen. Here are all my electrons, so what do I need to do? Well, there aren't any more electrons. I gotta form a double bond, right? But I got choices between these two. Which means that I'm gonna do this. But I can also have the resonance structure like this. Right? So, what's the bond order here? 1.5 between the two, but what's the bond order going to be on this one? Just 1, because this one's not involved in resonance, so this bond's going to be different than those. This is just going to be a normal covalent bond. So when we say all the bonds are identical, it's only the ones that are actually resonating or involved in resonance, sharing the pi bonds. Okay? It seems like there was one more on that. Oh, it's on the other page. Okay? Which structure is more likely to correspond with the actual Lewis diagram for the sulfate? What did you guys get on this one?
D.
D. Why D, Adlai?
I think I calculated. And you have the double bonds. Your charges become 0.
Okay, you minimize formal charge. So according to formal charge, it's going to be minimized in structure B. That's really the way you pick between the two. All of these things, single bonds are more stable than double bonds. Well, double bonds actually are stronger at holding things together more than a single bond. The number of unpaired electrons really doesn't matter. There are more possible resonance structures. Well, there are 2 possible resonance structures, but it's the formal charge that really determines which is the dominant structure. Okay? Now, you had one more. What was the other question I had? What's number 4? This one?
Yeah.
Yes.
All right, now we hadn't really talked about this, so this is good. This is a potential energy diagram for atoms approaching one another. So you assume, and this is two hydrogen atoms, so you assume hydrogen atom nucleus is right here. Hydrogen, that's hydrogen atom 1. Hydrogen atom 2 is slowly approaching from here. So there's basically zero potential energy, zero interaction with them. But now this electron starts being drawn to this nucleus. It's getting drawn stronger and stronger and stronger and stronger until we reach a maximum lowest potential energy. And remember always, lowest potential energy always means the most stable. The lower the potential energy always means more stable. That's why electrons fall back down all on their own from the higher to the lower. That's why exothermic reactions are more favored, because things want to give off energy and get to that lower potential energy state. Okay? Now, once it gets past here, now it's getting too close and the nuclei begin to repel one another. Until finally it's a very positive but strong repulsive force up here of the two nuclei. Too close. So there's too far away, too close, just right. So the bond length, if we had said what's the bond length going to be, it's going to be from the bottom of the well to right here. And we assume that it's just going to vibrate back and forth. The molecules are going to be coming together, moving apart, coming together, vibrating right in the bottom of this well, always. Now, generally speaking, single bonds are going to be shorter than double bonds. They're going to be shorter than triple bonds. Okay, I'm going to go find a problem though, but it has, it's a little trickier on that. Generally, the depth of the well is going to tell us the strength of the bond. The deeper it is, the lower potential energy, the stronger the bond's going to be. So a double bond is going to be deeper than a single bond. A triple bond is going to be the deepest. Okay? I'm going to show you an example of that. I'll pull it up. So the question is, at what point in the graph would a molecule of H2 be the most stable? Point C. Always at the bottom of the well. Okay, our one free response question was this one. Okay, when we did formal charge, oh, ouch. You are going to need to know that formal charge equation. When you do the formal charge, what's the formal charge on this carbon? It's going to be 4 minus 1/2 of 2, 4, 6, 8 minus 0 is equal to 0, right? This carbon, 4 minus 1/2 of 8 minus 0 is still 0. The hydrogens are almost always 0. They're all going to be the same. It's going to be 1 minus 1/2 of 2. There's never a lone pair equals 0. But the oxygen here is going to be 6 minus 1/2 of 2 minus 6 is going to equal -1. Okay? So, the oxygen has the -1. Here, carbon, again, this is going to be 0, right? But this carbon this time is going to be 4 minus 1/2 of 6 minus 2 is going to equal -1. And oxygen is going to be 6 minus 1/2 of 4 minus 4 is equal to 0. Okay? They both add up to -1. How do I decide which one is best? Okay? When you have the choice on which one's going to be the -1, somebody over here, what did Emmy say? The more electronegative one is the one that's going to be the favored one with the negative charge. Therefore, this is a more favored structure than this one. according to formal charge. Okay? That's a good formal charge question. What's the hybridization around each atom? What's the hybridization around the carbons? Put on like that. sp2. Okay? And really, hydrogen doesn't have hybridization, and terminal atoms coming in, you don't really worry about the hybridization. You just look at, and really it's going to be the carbons. Okay? Now, how many sigma and how many pi bonds? Well, how many pi bonds are there?
One.
Just one. Everything else is a sigma. So it's 1, 2, 3, 4, 5 sigmas. And then a hydrogen ion attaches itself to the acetyl ion, creating C2H4O. Draw the Lewis diagram of the new molecule. Well, where is the hydrogen going to attach? On the oxygen, because hydrogen and oxygen have a thing for one another. So you're going to end up getting C double bond C, H, 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 OH, because that's where your negative charge is on your favorite molecule. And then lone pair. Okay? Now, you would probably, well, I know you probably would. This would be the structure you want to do. All right. Got a couple of more for you. You have those actually already in your book. Okay, what I want you to do, you have those in your book too, I'll just show them to you. Princeton will be one with a multiple choice and one free response. Okay, on this one, I want you to do free response number 1. We just did number 2, that was the one that was in yours. And then on the next one, I want you to do number 4, which is another kind of boiling point chromatography one. Actually, let's just change that. Let's just do 3 on that second one, just for the sake of time. 4 is not as important. So do 1 and 3.
for those? They're still from the higher order. From the higher order. No. Yeah, and there's greater than the package.
Well, say that one more time.
Or which is that? Are you going to produce? Are you going to produce?
Yes.
I'm going to find out now.
Yeah. So, is that all we finished?
Yeah.
So nothing else for a second.
What?
Nothing else for a second.
What?
B.
What?
B. How do you feel in terms
Well, oxygen for sure is going to be a huge negative. And then nitrogen is going to be positive, and then this whole part here, whole oxygen is going to be positive. You know what I mean?
let's see.
Mm.
So that is vapor pressure. That red cap out of the over force. So vapor pressure was equal to atmospheric pressure, but the water started boiling, right? And this is like a substance starts to boil.
Yeah. Vapor pressure has a, is directly proportional to,
Atmospheric.
vapor pressure is inversely proportional to thermodynamic response due to, T2N, T2 having the strongest high mass, and the highest Johnson, and therefore the lowest vapor pressure.
Cool. So what are you gonna say?
Um,
good thing.
I don't know what it is.
Yeah, it's old.
My neck hurts. I know.
More blood for you, right?
Yes.
No. I will
All right, let's look at these, okay? So we have 4 substances, N-butylamine, propanol, pentane, and methanol, okay? Yes, they look very complicated, okay? But we just look at the structure. Don't get freaked out by the name and it's organic and I don't know, I've never seen this thing before in my life. We just look at the structures. All of the substances are liquids at room temperature. Organize them from high to low terms of boiling points, clearly differentiating between the intermolecular forces in each substance. So, what determines the boiling point? IMFs, the strengths of the IMFs. Okay? So, all of these are ionic, metallic, covalent, network, covalent, molecular. They're all molecular. Okay? They're all non-metal with non-metal. They're all just molecular things. Okay? What type of IMFs are going to be present here? You got hydrogen bonds here because of that, right? They all have LDFs, and if it has hydrogen bonds, it has dipole-dipole. Okay? What about this one? Obviously it has LDFs, and because of this right here, it's going to have slight dipole-dipole. What about this? LDFs only, and those are going to compare equally because it's 1, 2, 3, 4, 5, 1, 2, 3, 4, and then the carbon, but carbon and nitrogen are right next to one another, okay? About the same number of electrons. I mean, the electron clouds are very similar here, okay? And then this one, LDFs, hydrogen bonds, but this is going to be very polar, right? Very small, very strong hydrogen bonds. So, which one we want to go organize them from high to low? Which one do you think is going to have the highest boiling point? Okay? It's going to be, now this one's going to be a little bit trickier, and AP's not going to be quite this close, but you got this one and this one both have hydrogen bonds. Okay? This hydrogen bond, oxygen, is more electronegative than nitrogen. It generally is going to be a stronger hydrogen bond than this. However, the LDFs here are going to be much stronger than the LDFs here. But I'm still going to go, I don't know what the right answer is. You guys have it in the book. It's a butylamine, okay? And see, that's why it's just kind of a little bit tricky, because you have to compare hydrogen bonds to LDFs, and this one's just going to have greater LDFs. Okay? Then it's going to be the methanol. And then between these two, which one? The propanol, because we have the slight dipole-dipole attractions, and then this only has LDFs. Pentane, it is a liquid, but man, if you leave it open, it evaporates just like that. I mean, it's very, very volatile. On the methanol diagram, reproduced below, draw the location of all dipoles. Well, we have this right here. Where are the dipoles going to be? In other words, where are the charges going to be? Where oxygen is going to be the negative, and this is going to be your positive. Really, you're not going to have a whole lot over here on this side. This is more your non-polar side. This is going to be your real polar bond right here. I mean, if you put a positive here, it probably wouldn't be wrong. But you're not going to have any charges here. The reality is that this one's more electronegative than this, so the electrons are being drawn, kind of negating out even that positive charge here. What does the back of the book give on that one? on the carbon? Yeah, but I disagree with that. I'm just gonna go with this. Because there's gonna be a slight pull here, here, and here that's gonna negate any kind of pull coming that way. So the carbon's gonna wanna be negative from this one and positive. Anyway, this is the most important one. Is that the last question? N-butylamine is found to have the lowest vapor pressure at room temperature out of the four. Justify this observation in terms of intermolecular forces. Lowest vapor pressure. What does that mean about boiling point?
High,
We already determined that. Why is this the highest boiling point?
stronger IMF,
Strongest IMFs due to
LDS,
stronger LDS due to the long, flat hydrocarbon chain and hydrogen bond.
all that.
So the highest boiling point means the lowest vapor pressure?
Yes, always.
Doesn't like the part is that they would evaporate these, or do you have to have like the ones that?
Well, the question asked, no, that's fine, evaporate the least because we've got the strongest ion there. That's the same thing. Okay, explain the differences in properties given in the table above for each of the following pairs. The bond strengths of nitrogen and oxygen. What do we know? What type of bond is it in nitrogen
Triple,
versus a double bond? So it's gonna be stronger bond. What about bond length? Shorter. Okay? The bond lengths of hydrogen and chlorine, H2 and Cl2, bond lengths. Why is chlorine so much larger? It's chlorine's a much bigger atom than hydrogen, therefore the electron cloud is going to be farther apart, the bond length is going to be longer. Chlorine's just bigger than hydrogen. The boiling point of oxygen and chlorine. Oxygen's boiling point is negative 182, chlorine's is negative 34, much higher. Why? What's the only type of attractive force between the molecules for each one of these? LDS. LDS, they're both nonpolar molecules, so boiling points based on LDS. Okay, so that's what I would kind of put out there for this LDS. And so which one's going to have greater LDS? Because it's got a larger electron cloud, it's more polarizable, giving it stronger London forces. And use the principles of molecular bonding to explain why hydrogen and oxygen, this is a great question. How can, a miracle of science, how can hydrogen that's a gas and oxygen that's a gas come together to make water that's a liquid at room temperature?
Such a weird answer. He's not wrong.
He is not wrong, but exactly what does science say?
If you do it,
Hydrogen bonds are very strong.
Hydrogen bond does have to do with hydrogen bond. What type of bonds are present between hydrogen molecules?
Hydrogen bonds.
No, just dispersion, London dispersion forces. And hydrogen is one of the smallest of all molecules, therefore the London dispersion forces are the weakest of all, and they're already the weakest, and so it's the weakest of the weak. So they're a gas, hydrogen's a gas at room temperature. And you actually have to cool it down to near absolute zero to make it, I think its boiling point is 20 degrees Kelvin. What about oxygen? What type of molecule is oxygen? Polar or nonpolar? Nonpolar, so what's the only type of IMF? LDF. Again, it's a small nonpolar molecule, so it's going to be a gas at room temperature. But when they combine together to make water, what IMFs are possible? It's the ability to form those hydrogen bonds with one another. That's the difference maker. If it weren't for this hydrogen bond, water would be a gas at room temperature, and life as we know it would not exist. Life exists for from a spiritual point because of God, from a science point because of hydrogen bonds. The God of the science world. The hydrogen. If it weren't for water being bent and highly polar with the ability to form hydrogen bonds, water would be a gas, just like carbon dioxide, and life as we know it would not exist. That's powerful right there. That's a Monday morning brain-blowing concept. All right, I got one more question. I forgot to look it up.
Who did you say? Who did you say? Probably. The bond is the hydrogen bonds. Really?
Yeah.
We've experienced one with anyone. So are you oxygen or nitrogen? Okay, are we hydrogen? Stop. Okay. That fits me very well.
I can't find the question, but I'll be curious.
Does anyone have the ingenuity to do it?
I just wrote down.
Because we such a simple to me. That never happened.
Yeah, I sometimes forget this.
Yeah. That's unfortunate.
People not to ask you, so they'll never ask you to sit, help them.
Good idea.
Why do people ask me for notes from Friday? Oh, like at least.
Oh, they're not working.
Yeah. It's an awful lot for the class. They already have their class, their second period.
You jerk.
Wait, but how are they, oh, so you can see.
They should just help themselves, it's okay.
Okay, so you got three gases. This is the internuclear distance.
Alright.
So you got three gases, the three different color lines. They're all approaching one another. Okay, so this is, you got one of each of the three here. This is what the energy diagram is going to look like as they're approaching. Okay? Now, Need to make this one a little bit more shallow. Which one is which? Which line, green, purple, or blue, would you think is hydrogen?
Green.
Why?
Because it's single bond.
Okay? But I thought the triple bond is gonna be a shorter bond length.
Yeah, but I think it's cold.
Yeah.
But hydrogen is so small, that's right, this is what made this one tricky. Hydrogen is so small that even though it's a single bond, it's still gonna be really short. Notice the depth of the well is the least deep, implying a single bond. Now, oxygen and nitrogen are right next to one another on the periodic table, meaning what about their size?
Same size.
About the same size. So what's the difference in the type of bond between nitrogen and oxygen? Double versus triple. So the triple bond's gonna be shorter than the double bond. So you're gonna go hydrogen, nitrogen, oxygen. So the depth is gonna tell you the type of bond. Okay? When you compare it.